In this lesson, we'll use a deep neural network that learns how to classify images from the fashion MNIST dataset. This is what our network will look like. Let's go through this in detail. We can see that the input to our models is an array of length 784. This is because each image in our dataset is 28 pixels in height and 28 pixels in width. Since our neural network takes in a vector as input, these 28 by 28 images are converted into a one-dimensional array of 28 by 28, so 784 units. This process of converting a 2D image into a vector is called flattening. In code, this is performed through a flatten layer. This layer transforms each image from a 2D array of 28 by 28 pixels, each having a single byte for the grayscale, to a 1D array of 784 pixels. The input will be fully connected to the first dense layer of our network, where we've chosen to use 128 units. So this is what it looks like in the code. But wait a minute. What is this ReLU thing here? We didn't have to do that in our Celsius-Fahrenheit network. The thing is, this problem is more difficult to solve than the previous problem of converting Celsius to Fahrenheit. ReLU is a mathematical function we add to our dense layer, which gives it more power. In essence, it's a small mathematical extension to our dense layer that allows our network to solve more complex problems. We won't go into the details right in this video, but check out the text material below for more information. Finally, the last layer, also known as the output layer, contains 10 units. This is because our fashion MNIST dataset contains 10 types of articles of clothing, such as t-shirts or tops, sandals, ankle boots, etc. Each of these 10 output values will specify the probability that the image is of that specific type of clothing. So in other words, these numbers describe the confidence the model has that an input image is one of the 10 different articles of clothing. For example, the probability that the image is a t-shirt or a top, a sandal, or an ankle boot. So given this image, for example, the model could give us the following probabilities. As you can see, the highest score, 0.85, is given to the shirt label, indicating that the model is 85% certain that this is a shirt. Anything that looks similar to a shirt would also normally have high scores, and things that look very different would get a low score. Since these 10 output values refer to probabilities, if you sum them up, the result will be 1. Because given an input image, our neural network must tell us which out of these 10 it predicts it is. These 10 numbers are also called a probability distribution, or in other words, a distribution of probabilities for each of the output classes of clothing, all summing up to 1. So that's our network. Now we need the output layer to create these probability values for each of our classes. We'll tell our output dense layer to create these probabilities using the softmax statement. In fact, whenever we create a neural network that does classification, we always end the neural network with a dense layer that contains the same number of units as we always have classes, and always has the softmax statement.